Hello everyone. My name is Waleed, and I just want to ask first, raise your hand if you have any familiarity with multi-phase flow and porous media. Okay, good. So I'm going to talk about spontaneous imbibition in underground hydrogen storage. And what that simply is, for those unfamiliar with this, is that when you have a piece of napkin and there is water in contact with it, the water is gonna just spontaneously imbibe into the napkin. And this actually also happens with geological rocks. So if you have a water-wet rock and you want to use it for subsurface gas storage, then you inject the gas. And with time, due to pressure equilibration or due to buoyancy, the lighter phase is going up and there's movement of water, then you're going to have what is called spontaneous imbibition. So we wanted to study that experimentally. And we designed a novelty here using a porous plate. It's a water-wet ceramic porous plate with a high entry pressure. We use it as a boundary condition so that when we inject the gas from the top at a constant pressure, the gas doesn't get recycled again. So the invasion is going to be constrained inside the sample. And basically, the water-wet porous plate is going to act and mimic as an aquifer source, which is 100% free water level, just below the free water level. And we use micro-CT to look at what happens to the gas when you get the capillary pressure reducing due to the spontaneous imbibition. And these are some results. I'll try to fit in as much as I can in 5 minutes. But basically, when we injected the gas, the y-axis here is the gas saturation, and the x-axis is the saturation across the length of the sample. So you have initially, when we do drainage, injecting the gas at 12 kilopascals, you get about 90% gas saturation in the sample. Then we increase the pressure in the porous plate. Remember, it's at the outlet, so the water pressure is increasing and the capillary pressure is reducing. We reduced it to 8 kilopascals, and not much happened. But then when we reduce it to 4 kilopascals, you get significant displacement. So even though the gas is still at a higher pressure than the brine phase, due to capillary forces, the brine was able to imbibe and disconnect the gas. So when we reach near 0 capillary pressure, we followed by water injection. This time the capillary pressure is negative because the water phase is at a higher pressure than the gas phase. And we actually did displace about 16% of the remaining gas. So that means at the end of spontaneous imbibition, by the end of spontaneous imbibition, the gas is not totally immobilized. It retains some connectivity. These are some 3D images from the micro-CT. So initially, after we inject the gas, it's one color, one connected phase, one body. Then when we reduce the capillary pressure, you get some fragmented. You can see here in blue, the water is moving into the smaller throats and corners of the pore due to the wettability. Also, another thing we did is that when we waited for 48 hours, once we reach a capillary pressure of 0, so that both phases are at equal pressure, we waited for 48 hours and we saw better connectivity of the gas with time due to Oswald ripening or due to the equilibration of the capillary pressure across the sample. The contact angle is about 40 degrees when measured through the gas phase. You can see the gas bubble here in black, very spherical, trying to minimize contact with the surface, with the rock, which is in gray, and the brine here is the white phase. This is some poric you can see. If you are actually interested about all this, this is peer-reviewed work as well. Come to my poster over there and we can discuss more. Thank you very much.